We'll work on an example of using Coulomb's law to calculate the force on a charge due to other charges. So I've got three charges, Q1, Q2, Q3. Q1 and Q2 are both positive charges, and they're 5 microcoulombs. Q3 is a negative charge. Its charge is minus 5 microcoulombs. The distance that separates Q1 from Q2 is the same as the distance that separates Q2 from Q3. They're both 2 millimeters, and this angle theta is 30 degrees in both cases. So there's a lot of symmetry in this problem. So as things develop, you'll see that a lot of things are going to cancel out. The first question that we want to think about is, for charge Q2, what can all exert a force on it? So Q1 is going to exert a repulsive force, because like charges repel. Q3 is going to exert an attractive force, because differing charges attract. The important thing to note here is that Q2 cannot push on itself. It's a point charge. You can't take it apart. You can't directly add things to it. It's its own entity. It does not exert a force on itself. And that's going to be important because when we get to look at the form for Coulomb's law, this being a point charge, it is a distance of 0 away from itself. And dividing by 0 is going to make your calculator angry at you. So Q2 does not exert a force on itself. Alright, so let me draw in what forces are going to be exerted. So charge 1 exerts a repulsive force. So there's our vector to represent the force on 2 due to charge 1. 3 exerts a force that's going to be attractive, so it's along the line that separates them. And drawn correctly, this force should have the same magnitude. Because they're the same magnitude of charge, the distance is the same. So there is the force on 2 due to 3. Alright, to get the net force, I'm going to take the force on 2 due to 3, transport it parallel to itself. And so now I've arranged the vectors so that they're head to tail. And remember how to take the sum of vectors in the graphical method. Arrange the vectors head to tail, all the ones that you want to add together. And then their sum spans from the tail of the first vector to the head of the last vector in the sum. And so this is what we're after. We want to find the net force on charge 2 due to all the other charges. And in this case, there's just 2 other charges. So our sum, we're just summing 2 vectors together. Now going through and doing this carefully, this tells us a few things that are important. One is that just as much as the force on 2 due to 1 has a component up, the force on 2 due to 3 has a component down. So the y component of the force on 2 due to 1 is going to cancel out the y component to the force on 2 due to 3. And also, their x components are just going to add together. As far to the right as the force on 2 due to 1 takes me, then the force on 2 due to 3 takes me. So I can find just the x component of one of these and double it. So we don't have to do quite as much work. All right. So let's actually use Coulomb's expression for the magnitude of the force. So just to remind you of some of the notation. The force on 2 due to 1 in magnitude, so that's what the absolute value sign means. That vector magnitude is just as big as the force on 2 due to 3. And we can calculate that from Coulomb's law. So it's our coupling constant K, magnitude of charge Q1, magnitude magnitude of charge Q2. Now they're both positive, so these absolute value signs are not actually doing anything, but it's good practice to have it there because it's nonsensical to have a negative magnitude. And then it's an inverse square law in the distance. Okay. Our shorthand notation for the magnitude of the force on 2 due to 1 is just the variable without a vector sign. So this, the vector in absolute values, is the same thing as just the magnitude down there. We'll actually put in numbers. So K is 9 times 10 to the 9th. It is Newton meter squared per Coulomb squared. Q1 and Q2 for this problem turned out to be the same. So I'm just going to put that value in. So 5 microcoulombs is 5 times 10 to the minus 6 coulombs, and square it. And the distance is 2 millimeters, and I need to square that as well. So that's going to be 2 times 10 to the minus 3 meters quantity squared. All right. We look at units quick. The Coulomb squared in the denominator from K is going to cancel out this Coulomb squared once I square that term. The meter squared in K is going to cancel out the meters squared in the denominator. So this will be a force in newtons. Now, 2 millimeters is sort of a human scale distance. You can think about like how far that is on a ruler. 5 microcoulombs doesn't seem like a lot of charge. But as we'll see, this is an astoundingly large force once you calculate it. So it's going to be 5.6 times 10 to the 4th newtons. So not any sort of like extravagant distance. Doesn't seem like a very big charge. Gives you a whopping huge force. Alright, so as we described before, the y components cancel out, the x components add. So to get an answer for what the force is on 2 due to the other two charges, as a vector, I'm going to take the x component, which is going to be this side, the triangle. So that magnitude is 5.6 times 10 to the 4th newtons. I'm going to get its x component, so this is also going to be 30 degrees. So there's the x component of force on 2 due to 1. So we need to take cosine of 30 degrees, and I'm going to double it. And then it points along the x direction. This net force has no y component. So calculate that out. The net force on 2 due to the other charges is going to be 9.7 times 10 to the 4th